Good afternoon, everybody. Let's take our seats. My name is Tal Ellenbogen. I'm the Tal from the Faculty of Engineering. And welcome back to the session. I'm very happy to be the chair of this session because starting this session is our keynote speaker for this year, Professor Padgett.
Imagine now that I put a beam splitter in that beam so that I now have two identical copies. One of those copies goes up to the top and I form an image of the pattern on a camera. The other identical pattern strikes the object, and I use my single pixel detector, my single photodiode, simply to measure how much backscattered light there is. Now, the random pattern changes all the time. Whenever, by chance, the pattern looks a little bit like the object, the light level goes up. Whenever the pattern looks nothing like the object, the light level goes down. And I always know what the pattern is, and I always, but only know how much light is reflected. Well, as physicists, one recognizes that that's probably going to set up some kind of set of simultaneous equations. And as long as I use enough random patterns and I measure the backscattered light for each of them, I can probably deduce by some kind of inversion approach what the light would be. And that, in this case, it is monochromatic, but it needn't be. But it needn't be monochromatic. The important thing is that it's a pattern. I know what the pattern is, and I know what the backscattered light is. Now, of course, technology moves on, and rather than passing a laser beam through a glass screen to create a random pattern, there's another way to create a random pattern, and it's hanging from the ceiling. It's called a data projector, which if I just send random numbers to it, will project some kind of random crossword puzzle. And so now we move into what people would term, and this was a term christened by Jeffrey Shapiro in mid-2000, of computational ghost imaging, where I use, in essence, a data projector to project a random pattern onto the unknown object. I don't need to take a picture of the pattern. I know what the pattern is because I know what numbers I sent to the data projector. So I've eliminated the camera from the system. But I still simply measure the backscattered light. And so this, in essence, is a computational ghost imaging system where the ghost essentially refers to the correlation, the non-local correlation, not quantum, but nevertheless still non-local correlation, between the pattern over here and the pattern held, in our case, in the computer's memory. So just introduce some of my co-workers now moving forward, particularly Matt Edgar, that's worked with me for a few years now making these cameras, and also down here, Graham Gibson, who's worked with me basically my entire scientific career. So what might one of these imaging systems look like? So there I've tried to show a data projector. It is projecting a pattern, a random pattern in this case, onto an unknown object. And then I'm measuring with a simple single element photodiode the amount of light that is backscattered. Now, just to take a sideways step, what's in the data projector that's hanging off the ceiling? The data projector hanging off the ceiling, I haven't climbed up and had a look at it, well, I'm guessing it's based on a Texas Instrument digital micromirror device. And those are basically inside, there is a whole array of tiny, tiny, tiny mirrors which can tilt one way or the other way. They're all binary. They're not grayscale. So how does a data projector go about creating a video image which comprises of grayscale and color? The answer is it projects a lot of binary images very, very quickly. And so it's relying on the persistence of the eye to turn that black and white sequence into the right level of gray. How many patterns does it project every second? Well, that one's probably doing at 1440. 1.4 kilohertz, but you can certainly, with a little jiggery-pokery, make them run at about 20 kilohertz. So you can project binary patterns at 20 kilohertz with whatever light source you choose. You can use a white light bulb and get white. You could use a laser and get a color. You could use an infrared diode and get infrared projection. Because all they are is little mirrors. And so they work over a much broader spectral bandwidth than your silicon detector. So let's look at the object. This is now not 20,000 patterns a second. This is deliberately slowed down. But one has an object there. And then what you're going to do with your data projector is project a sequence of random patterns that you know. And for each of those random patterns, you're going to collect, measure the light that comes back. Now, inverting that data set sounds potentially complicated. And the thing that mainly makes it complicated is simply the size of the data. If you were going to do it by true matrix inversion, you would end up with a matrix where you had the same number of columns as you had pixels and the same number of rows as you had patterns. So if you're going to do a megapixel image, you would have a matrix of 1,000,000 by 1,000,000. And that would be challenging, to say the least, to invert. It turns out that you can do a pretty good job with a much simpler algorithm than that. And that is, I take the pattern, I multiply, which is a binary pattern of ones and zeros. I multiply that pattern by the analog voltage from the photodetector. So if it's a good pattern, I multiply it by a lot. If it's not such a good pattern, I multiply it by nothing. And so I just add the good patterns together, and I keep on doing that, and the result is quite surprising. So this is the object in the top left. Those are the patterns that I'm essentially projecting on it in the middle. That needle is going up and down as the amount of light backscattered goes up and down. And then I'm adding the patterns together, weighted by the backscattered signal. Now, there's all kinds of little tricks that one does here, in that when I say you multiply it by the backscattered signal, that's not actually true. What you do is you take the backscattered signal minus the average backscattered signal, so the number actually goes positive and negative, and it stops your computer overflowing its memory because the numbers don't get too big. And so one sees that once you add enough patterns together, one begins to get a pretty good rendition of the object. The obvious question is, how many patterns do I need? And we'll come back to that in a moment. But I want to just make another point before we get that far. So there we have depicted a normal camera-based imaging system. We have a light bulb. Light leaves the light bulb and hits the object. Light is scattered by the object, goes through the lens of the camera. The camera forms an image of the object on the film. And then you expose the film, or you read out from the CCD array, or whatever you've got in there. In essence, we are talking about exactly the opposite. So keep the lens in the same place. I'm not going to move the lens, but I'm going to unscrew the camera and screw on a data projector. And actually, if you buy your data projector from Texas Instruments, handily, the lenses are Nikon lenses, and therefore you can literally hold the lens in place, unscrew a camera, screw on data projector, and you effectively experience the world through the same lens. So let us do that. Let us replace the camera with the data projector. And now, the direction of light travel is being reversed. Now, the point I'm trying to make here is I have put the detector exactly in the same position as the light bulb. Now, why am I trying to make that point? The point I'm trying to make here is that not only is the image the same, but the shadows on the image are the same, providing that positioning of detector versus bulb is maintained. And so the strange thing is that you get images that look like they've been illuminated from the side, because that's where the light source was, even though the image is now being illuminated head-on and being detected from the side. The whole thing is reciprocal. And so it seems a little bit strange that even though the data projector is illuminating my face, I'll just say it again, illuminates my face straight on, I've still got a shadow down one side of my nose because the detector was over there and the light that hit this side from the data projector had difficulty getting there. So you still get shadows. And so the detector forms the equivalent of the bulb. And now just to show that these two things are the same, this is the lens, this is the picture through the lens, and here, very early image building up essentially the same picture through the same lens, but going from a camera system to a projection system. Now, I'm going to return to the how many patterns question, and this again also is a subject that's extremely old and well known to computer scientists and engineers and probably every other physicist other than me, but it was sort of new to me. And the postulation is this. How many people are in the room now? Let's say there's 64. I'm thinking of somebody. You're going to ask me questions, and all I can do is answer yes or no. How many questions is it going to take until you know who I'm thinking of? Let's assume there's 64 people in the room. So one question is, one approach would be 64, because I'm just going to go through. You're going to go, is it him, is it him, is it her, da-da-da-da. I'm going to go, no, 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 yes. But even my 10-year-old daughter would know that to be an extremely inefficient strategy. She would play a different approach, which is the person a man? I go, no. Oh, excellent. Now we've gone from 64 to 32. Does the person have black hair? No. And so on and so forth. So actually, you can see that there's efficient strategies providing you know something about the answer. I mean, when you think about it quite deeply, it's quite subtle. You think, well, hang on a second, there's 64 different people here. That's a 64-dimensional problem. How can I possibly reduce that to whatever, 7 questions or whatever? And the thing is, I was thinking of a person, not a superposition of different people. If I've been thinking of a superposition of 5 of you or 6 of you, the strategy of is that are they male, do they have black hair, when I can only answer yes or no is not a good strategy any longer. And so so my daughter clearly understands the concept of compressed sensing and sparse sampling and all that better than I do. Amazing she's only 10 years old. But anyway, so we always knew what sparse sampling was. How does that apply to images? Well, I could take an image of you now, and that on this phone would be something like a 5 megabyte image. Apart from by the time I come to email it to you, I'm going to JPEG compress it, and I'm going to send it to you as 250K. And yet the images would look virtually identical. So what is it about the image which is true? And what it is that the image is sparse in its spatial frequency. That's how JPEG compression. That's the assumption that JPEG compression makes. It's not the same as low-pass filtering. Low-pass filtering says, let's throw away all the high-value spatial frequencies. That's not what JPEG does. What JPEG does is, let's throw away the spatial frequencies that weren't very important. Some of those are high, some of them are low, some of them are medium. They're always different in every picture, but every picture has spatial frequencies which aren't important. Therefore, I'll just save them as 0. And that's how JPEG works. Let's apply it now. So the simple guess would be, if I have an image that contains 1,000 pixels, I would need to project 1,000 different patterns. That is the answer that you would do for raster scanning. I'd project 1,000 different pixels. And it's also the best answer you can come up with. If you are wanting to take a picture of a random object of which you know nothing, you cannot do better than 1 pattern for every pixel equivalent. But here, clearly, we've done much, much better. So on the left-hand side, I have the real object. This is the bottom here. I have a typical pattern. Here, I project essentially not 5,000 patterns, but only 2,000 patterns. And consequently, I've undersampled the space. My image has the appearance of noise. It has the appearance of noise for 2 reasons. One is there was actually noise on my data. So even if I'd done 5,000 patterns, the image would still be noisy. and the least squares fit is perfect, but it's noisy because, and ill-defined, because essentially it's under constraint. It's like I've got 5,000 simultaneous equations with 5,000 unknowns, but I've only got 2,000 bits of data. So what do? I work on the assumption that many of the spatial frequencies are 0, and once you do that, you end up with the image on the right. So bizarrely, actually, the image on the right fits the data less well than the image on the left. So I always find this quite amusing in that, you know, my entire life I always thought that we were, as scientists, driven by data, and we would fit data to a curve, and we would do a least squares fit, and somehow that's the gold standard. And of course, in the absence of any other knowledge, it is. But you often have other knowledge in the system. You might know, for example, that every intensity is a positive value. Don't get negative intensities. Well, that constrains the least squares fit. You might say, I know that I'm looking for an isolated object against a black background. That would be a stronger constraint. Or in the case of JPEG, you simply say that I'm looking for something which minimizes the participation in the spatial frequencies. And so again, I can run those kind of things through, and from a perfect fit, I can go to essentially a less perfect fit, but one with lower spatial frequency components, and the overall image improves from the top left to the bottom right. And I won't go into too much more detail about that, but I find it an absolutely fascinating subject. Now, clearly, had I done raster scanning, that's not quite so useful, because if I only want to do it with half the points, it means I get halfway down the image and the rest of it's undone. But by doing this projected pattern, I've got a little bit of information about every pixel, rather than a lot of information about a few pixels. And so that is a key thing. Okay, well that's fine, and you can see that one can build systems. Let's look at how you can do things slightly differently. Here is pretty much the same diagram as I showed you before, other than you notice we still only have one data projector, but now we have 4 detectors. Now, those 4 detectors, you'd think, maybe, will record the same data. But no, because the left-hand side of my nose is going to go preferentially into that detector, and the right-hand side of my nose is going to go into that detector. But nevertheless, the images are going to be geometrically identical. My nose is always going to be in the same place, because it depends where the pattern falls on it. And it's exactly the same if I now take a picture of you. Don't move the camera, don't move you, but I'm going to move the light source. So I'm going to move the light source here, light source here, light source there, light source here. I'm going to get 4 different images. It would have to be 3-dimensional in this case, but luckily you are. So it will, but not always. No, when I was paintballing, I can assure you this morning, I tried very hard to become 2-dimensional on the ground, well out of harm's way. I was lucky not to be shot by my teammates for cowardice. So can I just thank them very much for letting me hide behind a tree for the duration. I still got shot, by the way, but maybe that was actually one of my own teammates, I'm not sure. Anyway, so we see here now pictures, the 4 different columns are the signals coming back from the 4 detectors as the number of images goes up. And by the time you get to the bottom row, you'll see 4 high-quality images which look like they've been lit from different directions. They were all lit straight on. They were detected in different directions. And it doesn't take a rocket scientist to know, as you said, if it's 3-dimensional. If I subtract the left image from the right image, I get something that equates to the surface gradient in X. If I subtract the top image from the bottom image, I get something that equates to the surface gradient in Y. Since I know how to differentiate just about, I should be able to do something with that. So so computational imaging with one of the things. So here we see the idea of building up those images by adding the patterns together to give us 4 images that look like they've been taken from different directions. From those 4 images, I can make an approximation of what the surface gradients are in both X and Y. I think that's coming up in a second. So I get X, Y, and intensity. And then I can essentially, with some integration, again under constraints, reconstruct a 3D profile of, in this case, the polystyrene head, where actually it was done with a single data projector and 4 photodiodes. So I won't talk about constraints again. In this case, we constrain smoothness to go from the left-hand side, which is a fit based purely on data, to the right-hand side, which tries to minimize the second derivative of the surface. And then, again, we can produce our nice little surface mask, in this case, of a toy skull. Only a toy skull, I promise you. Now, we talk a little bit in science about creativity. I've become very interested in asking, where do ideas come from? And when you think that everything that we do as research scientists really is a creative discipline, your next paper is going to have to be novel. And so we now tend to play a little game whenever we get an experiment that works, which is we all sit down with a blank piece of paper and we simply ask ourselves the question, how could it be different? I've got an experiment that works, how could it be different? Not better, just different. We'll worry about whether it's better later. The first point is, let's be creative and write down ways in which it can be different. And so we did that game. And one of the things we wrote down was, rather than putting your detectors in different positions, maybe you should just put different filters on them. Maybe those filters are polarization. Maybe those filters are color. Clearly, they can easily be color. So now we project white light onto the scene, but measure the backscattered light in red, green, and blue. That was a blank one. Oops. That's not, it's come out as brightly. Little plastic dinosaurs. Can you just about see them? So that's a color image of some plastic, not real, dinosaurs taken with a single pixel camera. So you can see this is a pretty cool research grant. Not only do we get to buy the best Nikon camera money can buy, we get to buy plastic dinosaurs too. One of them was more expensive than the other. Now, this is where we were. This idea of projecting patterns onto the object and measuring the backscattered light. How could it be different? Oh. So all that we've done is interchange the position of the laser or the position of the light source with the position of the detector. It's like we've taken the data projector off the ceiling, taken the bulb out, and put a detector in its place. And then we've taken the bulb and illuminated the screen. But hang on a second, I don't need to illuminate the screen because the sun was going to do that for me anyway. And so now one takes an active illumination system using structured light into a passive system which is using structured detection. How can it be different? Don't use random patterns. Why? Because random patterns aren't quite orthogonal to each other. So they're a bit redundant. Let me use an orthogonal basis set. In this case, it turns out, for reasons I won't go into, the Hadamard set lends itself brilliantly to images. Why? Because most matrices don't matter at all. It is the sparse sampling set. So of all the Hadamard matrices that exist, actually, you can faithfully reproduce pretty much any image you've ever seen with about 10% of them. You never know which 10%, but roughly speaking, 10% of them. So this now was our first ever image of the system being used in reverse. That's Sun playing with his Rubik's Cube, where inside the data projector, there's 3 photomultipliers, one detecting red, one detecting blue, and one detecting green, and then the lab is just lighting him up. A walking robot. Slowly coming across the screen. See the Mac adapter in the back, just to give you some kind of scale. So clearly one can make all kinds of little camera systems basically based on a data projector, but then one is left wondering why bother, given that I've also got my phone, which is both cheaper and lighter than a data projector. Well, it comes back again that my detector in the data projector needn't be silicon-based. It can be shortwave infrared or whatever. So let us just move forward. So there, in the middle, you can't quite see it, is a little camera system, which is basically a mini data projector in reverse. And so that is a camera that works at 1.6 microns, and we bolt it onto the side of a microscope and go, hey, I've now got a very cheap camera that can see through silicon. And so these images down at the bottom there are essentially transmission images through a silicon wafer looking at the metallization both on top of and within the wafer. And actually the sequence of 4 images there at the bottom shows what happens as you reduce the number of Hadamard patterns. And of course, if you reduce the number of Hadamard patterns, it means you can either use each one you do use for longer to get better signal to noise, or go to a higher frame rate. And so this idea of being able to sample sparsely allows me to push the frame rate out. This is pretty much where my slide started at the beginning, which now makes a little bit more sense maybe. I've got the shortwave and infrared. It's got the shortwave, infrared, and the visible images. The reason why the visible one keeps on disappearing is because we had a smoke machine. And so we're all wafting a smoke. This is an undergraduate student. This is good use of undergraduates. We're all wafting our smoke machine at the undergraduate student, and he was sitting there in his sunglasses looking at the camera. But that's sunlight illumination. And the image on the top, which again you've seen before, is playing the same thing again. This is in the lab, showing him get color images. And then what's actually happening when you see the screen move across is that it's a 1 micron long pass filter, or 1.2 micron long pass filter. And so let me just forward wind to there. Okay, there we go. We're switching to the infrared, and you can see through again the tinted windows or the sunglasses. This actually is now my last slide, our very latest work. This is the latest version of the camera. I should say that my group has recently discovered the joys of having a 3D printer. The workshop are also quite pleased because we no longer keep on going to ask them to make things for us, we just print it. So actually, that whole camera system there is 3D printed, and it holds the lens and the detector in, roughly speaking, the right place, and indeed the digital micro mirror there on the back. And on top there, that's a very, very large British coin for scale. And now look at the images here. These images aren't so fantastic, but actually we're just illuminating the room with a comms diode at 1.6-ish microns. So it's active illumination in that sense, but not patterned. And what's that thing wafting around? It's the end of a little hose out of which is coming methane gas. And so the comms diode is tuned into the wavelength of the methane overtone absorption. And so we made a little video camera there, again, for the price of a data projector and a comms diode, which can see, in this case, methane gas. The top and bottom image is, well, okay, one of them's just image processed to accentuate the absorption feature of the gas. Now, whether we can really make it sensitive enough to be useful, we'll have to see. And then incidentally, I should say that this Quantic logo is the new logo of our imaging center that we've set up. So, we were talking earlier about I'm going to come and see your posters. I'm going to come and see your posters later. And let me warn you now that I'm going to ask you 3 questions. I'm going to ask you, what's the state of the art before now? Before you did this, what did people do? The next question I'm going to ask is, what did you do differently? And then the third question I'm going to ask is, well, why would I care about that? Who would care? Who would care about that beyond the authors? Well, clearly the authors always care. So I should perhaps reflect those 3 questions back on myself and answer those questions for this. And so, until now, most imaging systems, we're not the only people to play in this space. There's some fantastic work in Rice and other places. Most imaging systems rely on focal plane arrays containing many millions of pixels to do imaging. Our imaging system, or our imaging approach, uses, instead of 1 million pixels, it uses just 1. Why would that be of interest to anybody? It makes it very easy for me to make low-cost cameras in regions of the electromagnetic spectrum out with the silicon bandwidth. Okay, so that would be my what different and why bother questions. So I know I was late with my slides. I have got some copies of my talk on Glasgow University memory sticks, which I will happily give to you. You're at complete liberty to delete the talk and just use the memory stick. But anyway, hopefully I've got some more upstairs, but if you want one, just ask. Okay, thank you very much indeed.
Okay, thank you for a really wonderful talk. And let's have questions. Roy, one moment, I need to come in.
Wonderful talk, thank you so much. Can you do fast, when you record video, can you do some computational fast enough to understand the reconstructed image, so you will know which patterns it is beneficial to project in order to get the next frame in faster manner?
Yeah, that is in fact exactly what we do. It's not entirely trivial, A, because you have to think quite quick, and B, you don't actually tell the system what pattern to do. The system holds all the patterns in memory, and you can tell it which of its memories to display. So that means you can only work from a library of patterns that you have there. And so you can store about 40,000 patterns, and then you can randomly access those patterns. And so, yes, you can do it adaptively, and if all you want to work with is the base Hadamard set, that's good. But also, I haven't shown it here, what we also do is have some patterns where we have regions of interest, a little bit like your eye, has high resolution in the middle and lower resolution around the outside, where you can pull the same trick here, of course, apart from it doesn't have to be in the middle. And so we can say, actually, I'd like to take a closer look at the top left-hand side of the pattern, therefore I'm just going to display some patterns up there. But your ability to be sort of, the library set is limited by the memory of the device, which is about 40,000 patterns.
But wouldn't, if you would project the exact image that you already
so that would be,
that would give you just the difference of how it moved, right?
Yes, one can think about essentially projecting the previous frame back onto the scene and go, has anything changed? That would be an interesting approach, but you can't do that at 20,000 frames a second.
No.
Okay, but
here. Can you say something about the spatial resolution? Like, is the limit different when you use this computational approach?
No. So sadly, this is not, as I alluded to earlier, with all the fantastic work that's going on in microscopy, most of that is directed at enhanced super resolution, and that's fantastic stuff, and this can't compete with that. If you want a really high resolution image, then my recommendation is you go and visit the Canon or the Nikon store and you buy a conventional camera. So this, if you're willing to work around sort of 64 by 64 or 128 or 128, I think this is an interesting technology, as long as you don't want to go too fast. So the nice thing, again, that little camera that you saw at the end is quite nice because it actually has a visible camera built into it. And so what I will have is the high-resolution visible image, on top of which I will have a 128 by 128 shortwave infrared image. And at that point, you get sort of the location from the high-res image and the properties from the low-res. So I think combining hyperspectrally high-res visible with low-res shortwave IR in many cases addresses what you need.
You use the Hamarad filter to be more efficient with with a picture, but you can do equally well with illumination patterns.
Yes, yes. So, I mean, most of the stuff we do now is Hadamard. We tend to use Hadamards all the time, either for projected patterns, also for detected patterns. Now, again, another system that I didn't show, but is actually quite nice, is again in the question about how could it be different. Somebody wrote down, we'll use a pulse laser as our source, and our detected signal now will read with a high-speed photodiode. So as well as getting the 2D overlap, we get the 3D time of flight. And actually, when you do the inversion, you get the range of every pixel. So we've actually built a version of that camera on the projected active illumination thing, where you actually also get ranging information back from it, as well as positional information. And all of those systems, I was just using that as an example, would tend to use this Hadamard basis, which is certainly a good basis for your holiday snaps. If you were trying to do something like astronomy, it's probably not a good basis because the spatial frequency distribution is very different.
Let's have the last question.
Hi, thanks again. Two quick questions. What is the distance that you pictured the object, and what is the limit of the distance that the detector
Okay, so
works?
for the passive sunlight thing, so again, not shown here, I've got some pictures we took of the windmills in the shortwave infrared, and they are 30 kilometers south of our building. So we've got the largest wind farm in Europe. You can watch the blades come off, which they do. About 30 kilometers away. So it's just like normal photography. There's no limit to range. I mean, there's haze and aberrations and all those things degrade images. But in terms of image brightness, it's, everything scales. In terms of projected patterns, that's different, of course. And even with perfect matching, you've got a 1 over r squared issue. So the gas leak thing I showed you is actually just on the scale of the laptop. So at the moment, that's about 1.5 meters. But interestingly, although we're using a comms diode, it doesn't need to be particularly coherent. So we could actually just put 2 diodes or 3 diodes or 4 diodes or 10 diodes or buy a bigger diode. And then you're going to get the 1 over r squared. So if I wanted to come into this room and look and see whether there was gas leaking out of the pipes up there, I'm going to have to, with our current sensitivity, I'm going to have to use more than 10 milliwatts. I'm probably going to have to put out about 100 milliwatts of light, but it's not raster scanned, so it's not an iRISC, but you need a brighter source. So it's not magic, sadly.
And have you tried any other illumination except SWIR, like hyperspectrality?
So what? So we've done most different wavelengths in the sort of 400 to 2 micron region. Above 2 microns, there's 2 issues actually. One is that the chips you buy from Texas Instruments have a window on the front of them that doesn't transmit. Clearly, that would be solvable in the clean room. You could prise it off and put something else on. But also, the physical size of the mirrors means you get a diffraction pattern from them. And so actually, the current push on this technology to make the pixels smaller and smaller so you can fit more of them in is not what you want if you want to use it in the infrared. If you want to use it in the infrared, you'd actually quite like chunkier pixels such that diffraction doesn't get confused with the steering. So the steering angle is plus or minus 12 degrees off the top of my head. It's pretty standard for a micromirror. So you've got to make sure your diffraction is less than that.
Okay, so thank you. Let's thank our speaker again.